Dr. Saab, some much more earlier, the value of phenols was, I think, last slide. Value of phenols.
Okay.
Yeah, that one, sir. Yeah.
Okay. Okay, fine. Fine. So we were here. So basically, lignin can be converted to various different components, right? So the conventional paper-based products, materials, the low value, high volume application of lignin is simply in the combustion or gasification. That means you can actually use significant amount of lignin and only generate low value, which is simply the power, but you can generate high value components by using phenolics, and vanillin based derivatives can be derived. And of course, you can do these hydrocarbon conversions using lignin and produce, you can take these bio oils, biojet fuels, and then you can do a catalytic transformation and produce hydrocarbons. And basically, the value of lignin is here, right? You can see the value of the different types of lignins, but the value of the phenols is actually much higher than that of lignin. So that means, right, there is a great value proposition that you can bring in if you are going to convert, lignins to phenols, okay, rather than even converting lignin to energy, which is a low value commodity. Okay, and so here you can see, all these, the vanillin lignin carbon fibers have very high values, right? Whereas the typical petrochemical products have a low value. Okay, but their demand is high. So basically, right, you try to match the value and volume, and so even if you produce something at some, even if you're able to make a phenolic compound at some 20-30% selectivity, that is still going to be really valuable, and you make significant amount of money out of it. Okay, so typically coming to the pyrolysis method of converting lignin to valuable chemicals. So pyrolysis involves slightly higher temperatures of the order of 500 degrees, and that really involves three different phases in which the the reactions could occur. So you take a solid biomass, and when you subject it to a fast heating rate, so it can actually produce the primary liquids or aerosols, right? And these aerosols, when you're going to subject them to a much longer residence time or a much higher temperature, they can undergo secondary transformations and produce condensed oils or phenols and aromatic hydrocarbons. And you can also have a parallel pathway to form low molecular weight compounds like the permanent gases. And obviously, right, your char and also the aromatic hydrocarbons can polymerize to form much more amount of char, okay, which is sometimes also called as secondary char. It differs in the structure from primary char. So typically, with the increase in pyrolysis severity, that means increase in residence time and increase in temperature, you can actually shift the product distribution. Okay, so that means when you do a slow pyrolysis process, you get very high amount of char, whereas when you do a fast pyrolysis process, you get very high amount of the oils or the bio oil or the organics that are present in the product. Okay, and when it comes to the quality of this bio oil with respect to the crude oil, we can certainly say that the bio oil has a significant amount of moisture in it as compared to crude oil, because of the lot of the dehydration reactions that occur in the biomass, and because it contains a lot of these oxygenated organic compounds, so it presents a very low pH value. That means it is highly acidic, and so we need to and so its acid number is high, right? And because of very high amount of oxygen that is present in it, it presents a very low calorific value. And so this essentially means that you need to do a lot of upgradation of the intermediate bio oil. Okay, or in other words, if you talk in terms of the Van prevalence plot, right? So you have you plot hydrogen to carbon to oxygen to carbon ratio, right? So what basically happens is, if the lignin is basically here, it does contain significant amount of oxygen in it. And if you want to convert it to hydrocarbon-based fuels, right, you have to basically do this deoxygenation and hydrogenation step, which means you try to remove oxygen in the form of carbon dioxide, carbon monoxide, and water, right? And that means for every oxygen that is removed, there is also a carbon that is going to be removed, or for every oxygen that is removed by dehydration pathway, 2 atoms of hydrogen are going to be removed. Right. So that essentially means that we need to do a combined process of deoxygenation and hydrogenation using catalysts, so that we are able to produce hydrocarbon-like molecules or hydrocarbon-based fuel molecules, which essentially contain CH2 as the building block. Right. Then when it comes to the zeolite assisted cracking, right, you can actually use zeolites or acidic zeolites, and you can actually produce significant amount of aromatic hydrocarbons, which are like benzene, toluene, xylene, those kind of aromatic hydrocarbons from lignin. So lignin basically decomposes in a broad temperature range. So it produces it releases water, okay, typically around 100 to 200 degrees C. And at much higher temperatures, you can actually see the release of molecules like carbon monoxide, carbon dioxide. Hydrogen is released at much higher temperatures. And you will also see the typical, the rupture of the different bonds that are going to be present in lignin, right? So the aliphatics decompose in a range of 150 to 400, and the phenols and alkyl phenols are going to be formed from 300 to 600, and so on. And finally, you are going to be left with some amount of fixed carbon, which is the carbonaceous matter, or the polyaromatic hydrocarbon structures, okay, that are going to be formed from lignin, okay, during pyrolysis. And the typical oil or the vapor phase that is going to be released during lignin pyrolysis is going to it's going to contain widely different components. Okay, some are quantified and qualitatively identified by gas chromatograph technique. Some are going to be identified by HPLC type techniques. Okay, and there is going to be some amount of moisture and also some amount of this reaction water. So reaction water is nothing but the water that is released due to dehydration reactions. And finally, you're going to also have high molecular weight lignin derived compounds, which are mostly the dimers, trimers, oligomers, and so on. So the salient transformations in lignin pyrolysis can be summarized here. So the primary decomposition products include components like syringol, vinyl glycol, vanillin, glycol, and so on, which are the methoxy derivatives of lignin. But they can undergo dealkoxylation reactions to form what are called as simple phenols, which do not contain a methoxy group, right? And they are essentially phenol, catechol, and the methyl phenols. And you can also have the the dehydration reactions of the alkoxy phenols, which result in the formation of non-phenolic components from lignin. Okay, so I think I will actually I did speak about it. Okay, I'll quickly go through. So we have been employing some of these hyphenated techniques in order to understand the lignin transformation or the lignin pyrolysis mechanism, right? So this is analytical equipment. So that means we typically use milligrams, micrograms to milligrams of the sample. So we take the sample in a quartz tube, and then we subject it to pyrolysis in this pyroprobe setup. So we take this sample in the quartz tube, keep it inside the platinum filament, resistively heated platinum filament, and then we apply a fast heating rate of the order of 20,000 Kelvin per second. So that results in the evolution of vapors that can either be interfaced with GC mass, or it can be interfaced with an FTIR spectrometer, and so we can actually get the time resolved information about the vapor phase species that are evolving at very short time scales of the order of 1 second. Okay, so basically, we probed the lignin pyrolysis mechanism using PYGCMS, or the pyrolysis GC mass spec, and we could see that with increase in temperature, we observed significant change or typical trends in the variation of product yields or product distribution. So we could see that the glycols or the methoxyphenols decreased with increase in temperature, because at higher temperatures they basically transform to a wide range of these simple phenols. Okay, simple phenols, and further the simple phenols could also transform to aromatic hydrocarbons, and so we found very high aromatic selectivity at much higher temperatures. So this is like a summary that you have the primary products of lignin which undergo secondary transformation to form a range of phenols, and further to aromatic hydrocarbons. And we also observed we also probed the pyrolysis, the mass loss data. That means this is not really possible in a conventional thermogravimetric analyzer. So we measure we subject the sample to different temperatures at different residence times and construct these mass loss profiles. And we basically, once we get these mass loss profiles, we try to use different reaction engineering models to determine the the activation, the kinetic parameters, which are your activation energy and the pre-exponential factor. So in this case, we adopted a very standard standard model where alpha is the conversion, and then we adopted different models like first order diffusion models, contracting cylinder model, and then found out what are these different kinetic parameters. So we could determine the different the kinetic parameters based on the slope, right? And then fitted an Arrhenius plot, constructed an Arrhenius plot, and observed the different activation energy and pre-exponential factors, right? And then we also constructed a kinetic compensation effect or kinetic compensation graph, wherein we plot the activation energy and frequency pre-exponential factor from a wide variety of experiments, okay, that are reported in the literature, right? Because it's well known that the kinetic parameters vary based on the type of model that we use to derive them, or based on the heating rates that we employ to derive them. So in order to put everything on a single scale, right, and understand the typical the isokinetic relationship, this is essentially the isokinetic relationship that is going to relate the activation energy with the pre-exponential factor. We actually placed our result of the isothermal fast pyrolysis data, and we could see that typically the parameters are low, signifying that it is a diffusion limited process in a pyroprobe reactor. And it also, I mean, we get a reasonable the isokinetic relationship. So this essentially means that you can actually determine the values of alpha and beta, using which you can get the activation energy using pre-exponential factor or vice versa. Then we went on to get the time resolved FTIR spectra. So that means we get the time evolution of the FTIR spectra of lignin pyrolysis vapors with respect to time. So we could see that with increase in time, there is a significant amount of these functional groups that evolved, right? And we could see that we could actually do a much detailed analysis of plotting the peak intensities or the absorbance peak heights with time, and that tells us the rate of evolution of the different vapor phase components at short time scale. So you can see that this is typically of the order of seconds. Okay, so this means we sample the FTIR spectrum every second, and then we try to see at different temperatures what is going to be the kinetics of the gas evolution. So we see that at much higher temperatures, as expected, right, the maximum rate of vapor evolution occurs at much shorter time scale of 10 seconds, whereas it is slightly higher if you go to much higher, much lower temperatures. Okay. Then it is so the analytical experiments is all based on a very small amount of the sample, typically conducted in kinetically limited regimes. But typically, when you consider large amount of biomass being biomass or lignin being processed to generate significant amount of vapors, right? There is always going to be these kind of heat and mass transport effects that would affect the pyrolysis kinetics and the product distribution. So we have actually developed this microwave assisted a pyrolysis setup at our lab. The primary advantage of microwave being it's non-contact and energy transfer, which results in which basically results in lesser thermal gradients within the sample. So typically the sample heats up faster at the core, okay, than at the surface, and of course the temperature gradient is going to be not so high as you would see in conventional pyrolysis process. Okay, so that means more uniform heating, much faster heating, and so you get significant yields of the various products. So we could actually get something like 30% of phenol, 24% of cresol, right, and various other phenolic components from lignin. Okay, setup is pretty straightforward, and here we do an unsteady state experiment. In fact, so it's more like a batch process, right? So we allow the temperature of the sample to increase with respect to time, and then hold it at after it reaches a set temperature. And the feedstock was lignin of the total mass was like 100 grams, and we could basically see that we actually use different types of susceptors, right? Lignin and activated carbon based susceptors, and we observed the heating rate of the sample as the material is pyrolyzing, and we found that more the moisture content in the sample, right, there is going to be significant time that is going to be taken for just the removal of moisture from the sample, after which there is the increase in temperature is going to happen. So this was very evident when we use different mass of the susceptor. So you can see the mass of activated carbon that we use here, right? When we use less amount of activated carbon, that means lesser moisture present in the overall feedstock, we could achieve a much faster heating rate, as opposed to using a large mass of activated carbon and achieving a lower heating rate. And when we evaluate the typical product distribution from the pyrolysis of lignin, right, we could see that we got significant amount of this bio oil to the tune of 66 weight%. When we used large mass of susceptor, and that was primarily because of better control of heating that was achieved, right? Because when we use lesser amount of susceptor, the gas yields were significantly higher, okay, as compared to the oil yields. That's because of the reaction severity going much bigger, because we use lesser amount of susceptor per kilowatt of the energy, the power that is supplied, and that results in a higher severity of the process. Whereas in this case, we have a much lower specific microwave energy consumption, and so we get high yield of the bio oil. And the bio oil, if you really see what are its constituents, it does contain significant amount of the different phenols that are present in it. So we get like 40% of simple phenols, 20% of glycols, and syringols that are going to be present in the bio oil. And the other bio oils also had something like an equivalent selectivity to all these different products. So finally, we could see that the phenolic selectivity was substantially enhanced when we used some specific type of activated carbon of particle size 0.45 mm as compared to 1 mm, because extended surface also leads to better heat transfer and much better control. That leads to very high selectivity to simple phenol. So we could see that typically, syringols were very low, because the syringols undergo dealkoxylation to form glycols, right? And glycols can further undergo dealkoxylation and dehydration to form simple phenols, right? So that's a typical transformation that we observed when we did microwave assisted pyrolysis of lignin. right? And gas evolution during microwave pyrolysis is a very interesting phenomena, because we will see that the gases evolve at much lower bulk temperatures of the sample during microwave pyrolysis, because of the generation of these microplasma spots that are going to generate pits and pores within and cracks within the sample. Okay, and that's going to be the key for the release of hydrogen even at much lower temperatures of the sample. So we could see that hydrogen evolved in the temperature range of 100 to 300 degrees C. During microwave pyrolysis. So does other gases like CO2, CO, and so on. Okay. So I think I was just coming to this topic, right? This is about hydrogenolysis. That means, we use hydrogen in order to cleave the bonds that are present in lignin, and the objective is we could actually get, phenolic monomers, which are very much equivalent to C9 phenolic monomers, C9, C8, C6, C7 monomers from lignin. Okay. In fact, when we did pyrolysis, right, mostly we get, C6. Hydrocarbon C6 phenols from lignin, whereas we could get much higher order phenols up to C9 phenols when we do hydrogenolysis process. This is more like a process which employs hydrogen in order to cleave the bonds, right? So here you can see the typical mechanism wherein a beta O4 bond is cleaved, okay, by the use of hydrogen in the liquid phase. So the state of the art says that a wide variety of catalysts have been used in order to derive these molecules in a very selective manner. Okay, so there is a good amount of literature that is available, and what we basically did was we wanted to use a renewable biochar. Okay, that means we do pyrolysis, we get biochar. We took the same biochar, activated it, and used it as a support in order to embed platinum and metal oxides, right? In order to embed platinum and metal oxides in the biochar, and actually use as a catalyst for lignin hydrogenolysis process. So the objective was to prepare the activated carbon from biochar, right? Prepare this palladium-based catalyst, because palladium is a hydrogenation, dehydrogenation catalyst, and typically the metal oxides impart this Lewis acid character, right? And we essentially make our products of interest are essentially glycols, propyl glycol. So this is like C6 phenol, this is like a C9 phenol, this is C9, this is also a C9 phenol. Okay, we adopted standard impregnation process, right? We took biochar, which was obtained from the co-pyrolysis of biomass and plastics from microwave pyrolysis, right? And we did a chemical activation of the biochar in order to remove the inorganic impurities, right? So that actually resulted in reduction in ash content of the biochar from 23 to 4%, right? And then we added these metal precursors and also the palladium precursor, and did standard procedures in order to achieve metal oxide on activated carbon, palladium metal oxide on activated carbon. And the metal oxides were mostly tungsten oxide, molybdenum oxide, aluminum oxide, and zirconium oxide. Okay, so we got this biochar. This is the XRD of the biochar. You can see a lot of crystalline impurities that are present in the biochar due to the presence of silica, alumina, calcium, and all the other inorganic impurities. Then we did this activation process. You can see a very well amorphous carbon, right? And then we loaded palladium, right? We added palladium and tungsten, right? This is for pure tungsten. So you can see the salient peaks of the different the metal oxides that are basically marked in the XRD spectrum, right? And so we did a very detailed characterization, and what we basically found is that the surface area of the catalyst basically improved upon palladium loading in presence of reduced hydrogen ambience, and the average crystallite size varied in this order, and the molybdenum based catalysts were highly acidic than aluminum, followed by zirconium and tungsten. So we did detailed thorough characterization to establish these properties of the catalyst. So here you can see the typical TEM where all the plane reflections are marked, right, to understand the typical, the despacing of the catalyst of the different metals that were actually used. So this is for the basic activated carbon, right? This is palladium activated carbon. You could see the palladium spots that are present in it, right? Then palladium tungsten, palladium molybdenum, palladium palladium aluminum, right? This is palladium zirconia, right? Much more characterizations. We did XPS to understand the nature of the carbon that is present in the sample. We did temperature program reduction to understand the metal support interactions. I'll probably skip in the interest of time. But coming to catalyst activity tests, we took lignin, right? We added the catalyst in presence of methanol, temperature of 240 and 3 hours, right? Subjected it to the treatment in the autoclave, right? And after the process, we got the solid residue and the lignin oil or the liquid, right? From which we calculated the yield of the liquid and also separated it to analyze the different components that are present in it. So you can see the typical GCMS of the lignin oil. So you can see coniferyl alcohol as a major reaction intermediate, right? And the solid residue was also further washed, filtered in order to get the complete mass balance of the process. So we used a series of standard measurements to understand the mass balance achieved. And importantly, we did use standards to actually quantify each of these different components that are produced in the liquid phase from lignin, right? So one of the important characterization techniques of lignin is your 2D NMR, okay, two-dimensional NMR. That can actually be used to understand what are the basic constituents of the basic, the monomeric units that are going to be present in lignin. So here you can actually see that the major component that is present in lignin is the glycol, right? So you can see that glycol is you can actually see the signals corresponding to G5, G6, G2. All these are glycol-related components, and we also confirmed that this is going to be the major constituent present in lignin, right? And these were the products that were identified, not just identified, but were also quantified using pure compound standards. So glycol, isoeugenol, propanol glycol, propyl glycol, and so on. Okay. Coming to the yields and selectivities, right? So we got maximum conversion with aluminum-based catalyst, palladium on aluminum-based activated carbon catalyst, and we basically got very high selectivity to this product, which is propanol glycol. Okay, so the propyl glycol. So this is your propyl glycol, right? So what we basically postulated is from softwood lignin we can actually generate isoeugenol, propanol glycol, and propyl glycol, and there is always two parallel steps wherein your isoeugenol can get converted to propyl glycol, or propanol glycol can undergo dehydroxylation step to produce propyl glycol. Okay, and we could also see that the major products were like alkyl glycols, alkene glycols, alcohol glycols. Right, vanillin derivatives were more when we don't use any catalyst because it's produced through a non-selective cleavage mechanism. And by using a catalyst, we are also reducing significantly the amount of heavy products that are going to be produced during this process. And the extractives are also going to be significantly low with a catalyst like palladium on aluminum. Okay, so we did some optimization of the operating conditions. So typically 240 was found to be a good temperature in order to maximize the conversion and also the selectivity. So our interest was also to improve the selectivity to a specific product. Okay, and the temperature, hydrogen pressure, and time are the major factors here. So you could see that a time of 3 hours is going to give a maximum conversion and liquid yield. right? And here you can see the effect of time. Okay, so typically this is for the palladium on the activated carbon catalyst. Okay, without any addition of the secondary metal. So the maximum that we could basically achieve was about 21.5% of propyl glycol. Okay, that was actually the yield, right? In terms of selectivity, it was around 40% selectivity, right? That was a maximum that we could achieve. And with other catalysts like molybdenum, zirconium, and tungsten, we could actually achieve reasonable selectivities, not as high as what we achieved, using the aluminum catalyst. So you can see the C9 yield. Okay, the total amount of C9 monomers that were produced, okay, were actually shown here. So we could get about 20% of the total C9 monomers, from the other components, and their selectivities were typically the maximum selectivity that we could get was from the molybdenum catalyst. The maximum selectivity was about 57%. Okay, so the synergy was also observed. What if I'm going to physically mix palladium activated carbon and aluminum activated carbon, but we could still see that the catalyst had the combined catalyst had a much higher selectivity conversion, as well as selectivity to the propyl glycol product. Okay, and in order to probe, right, so these are the two alternative pathways that we proposed. Okay, starting from coniferyl alcohol, which we observed in our reaction sample, right? We observed that there are two alternate pathways for the formation of propyl glycol. So one is through dehydroxylation to form isoeugenol, and then hydrogenation to form propyl glycol, or we do a hydrogenation to propanol glycol and then do a dehydroxylation to propyl glycol. So this we try to probe, okay, using DFT calculations. Okay, wherein we took coniferyl alcohol as the optimized structure of coniferyl alcohol, and we try to observe the adsorption energies of this molecule over the lignin surface, over the palladium and alumina surface. And what we basically found is that the adsorption basically occurs, right, over the over the double bond that is present in coniferyl alcohol, right, which essentially takes it through the hydrogenation pathway, and then the subsequent dehydroxylation pathway to form the propyl glycol product. So based on this, we proposed an overall surface reaction mechanism, okay, wherein we have the first coniferyl alcohol adsorbing. So you have two different sites on the catalyst, like alumina and palladium, right? Palladium has the ability to adsorb hydrogen on it, right? So the first coniferyl alcohol adsorbs, right, and it forms propanol glycol here, right, through hydrogenation process, right? Once propanol glycol is formed, right, then there is going to be reaction with the alumina sites. So on alumina site, the adsorption is through this OH group, right? And finally, this results in dehydroxylation process to produce propyl glycol. So we could actually decipher the complete mechanism of formation of some specific monomeric products from lignin, okay, by a combination of experiments as well as simulations. I think in the interest of time, I'm going to skip some 10 slides, but I'm going to stop here. And if you have any questions, I'll be happy to interact. Right. So the concluding points are that certainly I've not really talked today about the last 3 points. Right. Right. We did some experiments using solvolysis and also sonophotocatalysis to convert lignin to phenols, but I think I did discuss in detail about what is lignin, what are the challenges, what are the products, the value addition that you can get from it, what is the fast pyrolysis product distribution, and I did tell you some of our results about the pyrolysis FTIR to probe the time scale of evolution of the products from lignin, right? And then about the microwave assisted pyrolysis, that was discussed in detail, right? And then finally, I talked about the hydrogenolysis process, which is mostly our recent works, which say that we can derive, selectively, we can actually derive C9 monomeric phenols from lignin. And that's going to be a key because that means that we are actually able to generate significant value out of lignin. So with this, I thank my students who do all the work and some of our funding agencies. And I'll be happy to take any questions in the last 5 minutes to 10 minutes.
Participants, do you have any questions?
Ma'am, I have one question.
Yes, sir.
Sir, how DEFT is implemented in this part in the case of hydrogenation, dehydrogenations?
How? I didn't get you.
In last slides, you have seen the DEFT calculation in these slides.
Yeah.
How it is calculated? As I said, palladium 111, aluminium 111.
So the palladium and aluminum 111 phases were actually derived from our experimental characterization of the catalyst. Okay.
Okay, this is XRD calculation, sir.
No. I'll tell you. So the XRD tells us that palladium. You could see the slide now.
Yes, sir. Is visible now.
Yeah. So the XRD tells us that okay, so here you can see. So the palladium 111 is basically exposed to the surface, right? And also from these studies also we could see that TEM also we could see that aluminum 111 and alumina 111 and PD 111 are essentially exposed to the surface of the catalyst. So the calculations were done taking that the coniferyl alcohol intermediate is going to get adsorbed onto those specific planes of your catalyst. So these planes were basically structured on as the top surface, right?
Yes, sir. Sir, in ultrasonicator, have you faced some problem in the separation of cellulose, hemocellulose, and lignin part?
We actually used only lignin. We only used lignin. We did not use actual biomass, but that is, we have done it. But in this study, we have used only lignin and then seen how lignin gets transformed to phenolic components.
Any other questions by the participants? Anybody else would like to ask questions? Very sorry, we know that you got disconnected from us.
That's okay, madam. That's okay. No problem.
You gave a really nice talk, especially the chemistry behind all those reactions that were occurring, where the cleavage was going to occur and so on. It was really interesting. I hope the participants also benefited from this because I guess this is one of the, this is supposed to be a part of sustainability, right? So that you don't waste anything and you can recycle and get new product. So I think if the participants have observed or listened to his talk carefully, then they can find out different places from which to pick up points to start working on. So I thank you once again, Vinu, for giving us such a good talk. And if there are no further questions, then I think we can call it a day today, because they've had a really long day from 9:30 in the morning. I think it has been going all over. It has been going for over 2 hours. So thank you once again, Vinu.
Yeah, thanks,
And,
ma'am. Thank you. Thanks to
yeah.
all.